Hello, Professor
Hey,
Nelson.
Vijay.
Good.
Hey, so I think we're waiting for Q.
Mm-hmm. Hi, Q.
I see.
Yeah, so it looks like that. So you were able to get the new dialyzer there, right?
Yeah.
So what is this? What dialyzer is this?
Let me go ahead and share my PowerPoint.
Yeah.
So there are two Nipro Elisio 17H and 12 of the Viva Clear capillary dialyzer 300.
And so there's a Riva Clear.
Yeah. Viva Clear and the Nipro Elisio. And the amount is 2 of the Nipro and 12 of the Viva Clear.
Okay. So yeah. Okay.
Mm-hmm.
And so these are relatively new dialyzers, right?
Yeah, they are like currently by Nipro and Baxter company, and I think the good thing is about this dialyzer is really they're already being tested. Like for the conventional, which is the inside out convention, they have been like fully tested, and the capacity is like fully developed. Let me go ahead. So for the Nipro, for the myoglobin, so about 16 and 17 kilodaltons. The seeding coefficient is about 0.22. So
Mm-hmm.
so that gives me a feeling that this one is pretty close to our Rexy 21R actually, because I kind of
Mm-hmm.
feel bad that like we are not able to like measure the exact like pretty accurate for the destran on the UV VIX, so that like Professor Clark said there might be like a low flux dialyzer, but in fact it's just that we can't like quite measure the destran yet. But I feel like the Nipro is pretty close to the Rexy. That the Nipro is about 17 surface area, and the Rexy is 21R is 21 2.1 square meter.
Mm-hmm.
And for this one, the Baxter, the River Clear, is only about 1.4 of the surface area, 1.4 meter square, and it has a little bit larger. I'm not quite sure yet because the microglobulin and the myoglobin there are quite a lot of the molecular weight differences. So for the
Mm-hmm.
microglobulin, it's about like 11 or 12 kilodaltons, and for the myoglobin, it's about 16.7 to 19. So
Yeah.
there's yeah, but I think those are like the two like benchmark for middle molecule clearance
Mm-hmm.
and Stephen coefficient.
Mm-hmm.
Hmm. Yeah, and I think I also go to the Whistler Center, which is
Mm-hmm.
the right next to the Nelson Hall, and at the
Yep.
yeah Dr. Evans. So he's like one of the two people that talked to me about the
Yep.
HPLC. Yeah,
He's actually a really nice person. I've met him a couple of times.
yeah, yeah. So he's like Anton is more like a employee, and Dr. Irvin is like a faculty at the resource center, and he like taught
Yep.
me like how to use the machine, the benchmark refractometers he had
Mm-hmm.
in his lab, and yeah, actually his refractometer have about 4 digits of a resolution, and I test my destran with like 2 gram per liter, 1.6, 1.2, 0.8, and zero point 0.4, but the RI readings I get are pretty similar. They are like it's hard to tell the differences between them, and I think the
Mm-hmm.
reason is because since the resolution is not high enough, so and also the accuracy rate is also pretty large. So I think for the Destrin 10K, the R reading is all within the accuracy range. So that's why I can't like quite get the differences between a different concentration level.
Mm-hmm.
And the one that I like guaranteed like or require from the Atego that I probably get it by the end of July is the Atego RX 5000i. It has a little
Mm-hmm.
bit higher resolution, up to 5 digit of resolution, but the accuracy is still quite large. So what I'm thinking right now is we probably like can't get really exact differences under really small concentrations. So for example, under zero point 0.2 gram per liter, it might be really hard. So it is. I'm feeling more confident when we're using the RI detector on the HPLC. Then I'm pretty certain it can get like tell the difference from the clearance experiment for this low concentration of death-strand. Mm-hmm.
So just repeat the last.
Yeah, I'm sorry.
So
Yeah.
So it sounds like Dr. Owen's lab. It looks like the refractometer does not give enough resolution
Right.
to be able to discern different concentrations of 10K dextran.
Yes.
Okay, but this one from Atago
Mm-hmm.
has slightly better resolution, but you're still not confident that it will be able to.
Yeah, I'm not very confident that it will like.
For 0.2 grams per liter.
Yeah, this is for 2 gram per liter. I also prepare some 0.4, 0.2. I haven't like tested on Dr. Owen's lab at high concentration. It's not working. But if for higher resolution, if we can like we have like one more digit of a resolution, I'm not sure, but since its accuracy range is quite large, it's 0.0004. So I would trust more on the RI detector on the HPLC system that I believe it can give me like higher of a resolution with the graph.
When you say the RI detector on the HPLC, is this like
the one at the lower at the research center? Yeah.
I see. Then that one's different than this art. That one's different from the toggle.
Yeah. Those are the ones that are in line. That is like we'll measure. So we have an HPLC system. So the RI detector will measure the RI for the whole length of the tube. That will give you a graph of like what it's gonna look like. Yeah.
So you're confident that the one in RI detector and lower is going to be able to.
It's gonna be better than this one. But if it's actually
then either this one or the toggle, you're saying.
Yeah, either the lower or the Whistler Center will work.
So what is the? Can you remind me again? What is the resolution for the one in lower?
Yeah, it's the Narnos. It's since they used like a different unit from the refractometer, the benchtop ones. They use called the NRIU. Is I would consider the accuracy to like equivalent to 0.0001. This is like what they can do and give like a pretty accuracy. But I haven't like do any calibration on the lower center, so those are just the words from the literature. I have to like do the calibration at one of the facility to be able to like do the calibration and see if they can like measure or capture the clearance at like different concentrations. Mm-hmm.
Okay.
Yeah, but I will present like the methodology when I actually like get my hands on HPLC and also the sieving coefficient experiment later. Mm-hmm.
Yep. So I think that makes sense. Then the lower makes the most sense.
Yeah.
Going forward. Mm-hmm.
Yeah, and regarding the email I sent you earlier this week regarding like if we can't get the dialyzer or something, we can go forward with the Rexy. So my question now would be like, since we have like more dialyzer, a general question is like how we want to do with it, because it has like a more specification and details and also experimental data with it. So do we just want to skip the Rexy 21R and go with one of the Vivar clear dialyzer?
Yeah, I think we should do experiments with Exceed anymore.
Okay.
We can do it with these. Because these are the ones that are more I think what Bill says, these are the ones that are more clinically relevant.
Yeah. Those are people.
Right, we can go ahead and do the same type of measurements, right?
Mm-hmm.
You can do inside out versus outside in.
Exactly.
Transfer, measure the clearance. You can measure also the sieving coefficients.
Mm-hmm.
One nice thing is the sieving coefficients are I believe, they're specified already for a lot of these things. So you measure in your setup and see how accurate it is compared to what's reported.
Right.
Give you confidence in some of your measurements.
Yeah.
Right?
Yeah, I think my next point is about the accuracy of my sieving coefficient experiment that in my lab setup. So I'll just jump right to it. So, we do you want me to zoom in to see better of the PowerPoint?
Yeah, that's fine.
So yeah, for my seeming coefficient experiment, this is a diagram of what my lab setup currently is. That we have a blood side entering, dialysis entering here, exiting. So for the blood side, we can do pass or recycle. And here, dialyzer. So for the seeming coefficient experiment, we will shut these two valves down, so they will be go up to from starting from the blood and directly penetrate through the membrane and then exit through the line here. So after we shut this down, we will probably considering the ultrafiltration rate of 30, 50, 75 to 100, because this is not like a hemodialyzer that is going through all of the stream flow will directly penetrate through the membrane. So we were considering a lower one, like what we would use for ultrafiltration rate clearance experiment. But the thing is, regarding the pump here, the minimum flow rate is 80 milliliters per minute. So we can't go below this number. So what I am thinking right now is do the 80, 100, and 120 milliliter per minute for the ultrafiltration rate.
That sounds fine. Yeah.
Yeah, and regarding the procedure, so can I go back? So we will first wash the system with the 4 valves open, so that we know that the tube here and the tube here, because they're all connected, even when it's like shut down, this tube, this space, this area will still connected to the flow. And I will wash it before the seeming coefficient experiment. I will wash all of this, and then I will shut the 2 valves down and leave the 2 valves open, so that that means some of the liquid will still stuck up top. So because of the surface tension, and what we're doing here, this is like a diagram for the detail of the hemodialyzer itself. So basically the blood in, and they will penetrate. Oh, my bad. They will exit through the pore, the membrane, and from what I was seeing, the blood will only go up to here when we're doing the seeming coefficient, and this area will be air bubbles that will kind of like disconnected from the blood line here because of the high pressure. Since like we block the 2 valves, the pressure at the top will be really high. So when we are putting water from the blood in here and exiting through here at outside, it won't go up really high. So that we won't have to worry about what do I say, like contamination from this valve. And I will run the system for quite a long time. So I mean, this seeming coefficient experiment will reach the steady state, which is after the purging of like all the original solution, and the outlet concentration, that outlet here will be constant, so that we know we reach a steady state. Does it make sense? Okay. So that
I think it makes sense, and I just want to get your thoughts. Do you see any issues with any of these?
No, I didn't see any issue.
Okay.
Yeah,
just wanna make sure.
actually discussed with Q on Monday about the setup, and I'm going right to, yeah. So that's when we're doing the seeming coefficient experiments. You enter here, exit through here, and it's gonna penetrate the membrane. And so this is the bottom side, and at the top side we can see this area or space are still connected, but they are not like contacting the liquid or flow through the seeming coefficient experiment, so that we don't worry about it. So this is a picture taken from a conventional mode setup, and for the outside in setup, the top part are still not like it's gonna affect or connected to the flow. That may be because of we are using a pretty lower flow rate, which is only 80 milliliter per minute. Maybe when I go up to 100 or 120, they might be like, so that the top part may have to like connect, but after like purge a long enough of time that it reaches steady state, we shouldn't be worried about the effect of these problems.
Okay.
So yeah, so that goes straight to our research question regarding the sieving coefficient experiment, which is like how long for the system will reach the steady state. So how long should we like purge the system? So that's the first questions. And after we get the overall sieving coefficient of the membranes, what would be the sieving coefficient for each layer of the asymmetric membranes, right? And so we will answer this research question by getting the ultrafiltration rate, different of ultrafiltration rate, and in conventional mode and outside in mode. And I will explain this a little bit more later.
Is alerting ultrafiltration affects?
Yeah, I'm sorry, it's altering. Yeah, it's what I'm meaning is altering, just changing the ultrafiltration rate, like from 80 to 100 to 120. Yeah, that's my bad of spelling here.
Yeah,
So
I mean, as long as you don't have much, so I imagine as long as you don't have much fouling, I don't think it should affect the sieving coefficient.
yeah, the thing is, I feel like the sieving coefficient might be
Well,
like
okay, no. So, it can affect it. There is, because the sieving coefficient is essentially 1 at 0 of ultrafiltration rate.
yeah.
It's 1 at infinite ultrafiltration rate because of concentration polarization, right? And in between you get like a different sieving coefficient, right? So you're gonna get, I think we showed in the paper, right? We wrote. So the sieving coefficient that is observed is a function of the ultrafiltration rate.
Yeah, exactly. So that's why I'm trying to get that relationship.
It's a function of ultrafiltration rate, and that's because there's like 3 different sieving coefficients. An observed, there is the actual sieving coefficient, and there is also an asymptotic sieving coefficient, right?
So what I'm showing here is go ahead. So
Go ahead.
What we're getting is the observed sieving coefficient, which is just the filtrate divided by the bulk area, which is the inlet. And we will use this relationship to get the actual sieving coefficient with this relationship here. And the JV here is the flux will be determined by the ultrafiltration rate. When we have a higher ultrafiltration rate, we get a higher flux. And we will altering the ultrafiltration rate, which will change the flux rate and see like the differences of the actual sieving coefficient. And yeah, I'll continue. Yeah, I will actually elaborate on this topic later. So the first question is like, how long should we purge the system or to reach a steady state? So currently in my lab, we only have the vitamin B12 and the myoglobin. I have reached out to Joe on Tuesday, and yeah, he said he can't find any like relating purchasing history from Fasar. So I give them our project name and company and the account. He can't find anything like that relating to the.
So actually, it was purchased through not this account, right? This NovaFlux account, because we didn't have this account before.
Oh, okay.
Yeah, so it would have been through my startup.
Oh yeah.
Account.
So that's why.
You may want to inform them of that.
Yeah, so that's what Jill says. She would like look at your startup account and try to find.
Yeah, because Farzad, we didn't get NovaFlux funding until after Farzad left.
Oh, okay, I see. I understand. Yeah, so we will probably like do what I'm going to explain, like what I do with it. Vitamin B12 with the myoglobin. It's pretty similar because we will just measure it using the UV-Vis. So for the Dastran, we will be utilizing the RA detector. Then I'm going to talk about that later as well. So that's what I've been doing with the vitamin B12 in the conventional mode at the UF ultrafiltration rate of 80 milliliter per minute. And so we observed that. So after we purging, so at the first few minutes I don't record it because the concentration is not even close to like being at the steady state. So and when we can see as time move on, so this are UV readings, and the solid color red line here are the inlet concentration of the vitamin B12, and the increasing line are the outlet of the vitamin B12 concentration. So when we are close to about 20 or 21 or 22 minutes, we will see that the receiving coefficient is about 1, which is like reaching the.
Why is this data like so jaggedy?
So do you mean the steep curve here?
Yeah, this orange curve or whatever on the left.
Yeah.
This is for the outlet. Why do you sometimes see it, for example, go above the inlet concentration and sometimes go below? Like, I'm trying to understand what's going on here. Why do you see such large fluctuations?
Yeah.
In the outlet concentration?
Mm-hmm. Yeah. One explanation I get is the capsule or the quads that we put into the UV VIX. They are all plastic and they are stored in together. So we will reuse it. We clean it and then we reuse it. The problem with the quads is they might get dirty and they might there are maybe some scratches on the surfaces that will affect the readings. So that's what I get. There are certain viral quads that is not shown here. It gives a really high value, about 1.15 or up to 3 for 2 of my experiments. So I get rid of it. So I was thinking, so this viral, the capsule, you can see as most of the time they are pretty steady. But this 3 virals typically might have some scratches, or they are not very clean on the surfaces, or they are not like dry enough. That might cause this problem. But as you can see, there are total of 22 of the virals. Only like 3 of them are not giving like a very correct result that we can see from the trend line.
I mean, you also have 21 and 22 minutes also it is above the.
Yeah, that's what I'm trying to say, that the timeline here I use is not long enough to reach the steady state. So so we know that the receiving coefficient of the small molecular vitamin B12 should be about close to 1. So at this stage is actually pretty close to the one after the 20 to 21, 22. So what I'm seeing in this experiment is that the time for purge is not long enough. And in the next experiment, I will show you a much longer time, which is up to 27 minutes. So we can see, we can also observe these like 3 virals. I'm not sure because we have like multiple orders. I'm not using the same virals for first minute, same viral for second minute. So we still have like some this. Yeah, I would think.
So I want to ask, so where are the scratches and like what, and how are you guys cleaning it? Because I don't think Farzad had any of these issues when doing UV vis. So I'm trying to understand what happened to the quartz files.
Yeah, so I'll show you. So this is the what we're supposed to use, the micro quartz viral for the UV VIX, but there are only like a couple of them. I believe there are only 4 of them, and since we have a lot of sampling, we are using these plastic vials that's for bought. There are 40, 50 of them. That is like really, really light and really like easy to like leave a scratch or be dirty on it, and it's hard to clean the inside of it. So I feel like that's the main reason causing the slight curve because of the deflection of the light.
So you're not using the quartz vials that are recommended by the manufacturer.
Right. Yeah.
Okay. And if you use the ones that are recommended by the manufacturer, do you run into these issues?
I would anticipate that I don't run into this issue. Yeah. Because
you have not, but you have not used those.
I have not used those like. Mm-hmm.
Okay. So the question is then, okay, if you use those vials that were recommended by the manufacturer, would you run into these issues where it's not so jaggedy? And you may not have to sample every minute. You can sample every 5 minutes or 10 minutes,
Mm-hmm.
right? And
Yeah.
see what you get. Mm-hmm.
Yeah, I can definitely try to like find out if that makes a difference. Yeah, for sure.
Yeah, and also like how expensive are these quartz vials?
They are. I believe they are. From the quality and the texture, I believe they would cost about $50 per set of two.
Okay. I mean, if you want to buy something like that, it's okay, right? I mean.
Yeah, but I feel like this single perk we can just ignore it because we know, like for when we go to a longer time, it will pretty close to one. And the thing about the UV VIX, it will have like so for example, the value here is like 0.44 or 0.45 and 0.46. When I'm using the viral, I haven't used the micro quartz, but when I use these plastic virals, when I tested the first time, it will give you like 0.44. The second time, it will probably give you 0.45. So there are some accuracy problem with the UV VIX. I haven't tried the micro quartz yet, but that's what I came across. So I feel like I just want to give a rough idea of like how many minutes of the purging when it will reach a steady state.
And I want to ask you, and then for when Farzad did the experiments with vitamin B12, when he was looking at clearance, what type of vial did he use?
He didn't mention, but he using a bunch of the virals. I think, yeah, here using. Yeah, he will take sample from like 0 to 15. So I don't think like, if you are trying to use this, we use this viral, you have to like get some sample of it, get the number, and then clean it, and then dry it again, and then add another sample again. So that will like doesn't make a lot of sense to me. And so I would think that they are using this small virals and collect a lot of sample at a time, and then put it in the UV VIX and get the values. Yeah, I can.
Yeah, so I mean, you're probably right. It does take over 20 minutes. That's fine.
Yeah. So yeah, I'll double check with Fasar with like what exactly a procedure they use. But for the vitamin B12, so the time to reach a steady state is about 20 or 22 minutes. And I think that will be likely the case for the myoglobin and dextran when we're doing that. So I would probably set the time to 25 minutes as like a safe time to purge it to make sure they are already a steady state. And the other thing is about the vitamin B12, since like the total sieving coefficient is 1, and meaning that both layers of the asymmetric membrane, they are both 1. So he can so the B12 can penetrate the first layer, no problem, second layer, no problem. So together they are 1. So we can't get.
Sure.
Yeah, so and we also think that for small moleculars, like increasing or decrease the UF ultrafiltration rate will not affect the sieving coefficient. So it is 1. No matter if you increase it, it's faster. If you lower it, it's slower. It's harder, slower to go through, but the sieving coefficient is still going to be 1. Regarding so that means this number is not going to have any effect on the SA of the vitamin B12. That's what I'm trying to say.
Yeah. I mean, it's going to be probably close to 1, but
yeah.
I mean, I think it'd be good to make sure you're still much more confident in your measurements, because ultimately, all this measurements you're going to be doing for concentration are going to be through UV. So you need to be confident in your ability to record, absorbance correctly. going forward, right?
Right. Yeah, maybe what I can do next time is because the initial concentration is always the same and it's really important. I'll probably use the micro quads to like get that number for the inlet, and for the outlet I will because I can because I have to wait like 22 minutes. If I do like a 5 minute sample or a 1 minute sample, it's gonna be the same for me to just wait there. I think I feel like this method is giving like a pretty good idea because we know we are slowly increasing the concentration. It slowly move to the steady state, and when it moves to the steady state, although there are some fluctuations, but we know that it's already at the steady state. If that makes sense. Mm-hmm.
Yeah, so you can take one, 20 minutes, 30 minutes, or something like that.
Yeah.
Hopefully by 30 minutes you're like at steady state.
Yeah.
I think that's going to be fine, but you should just make sure you're confident in your measurement. Because if you're not confident in doing your UV vis, then I mean you can't be confident in any of the clearance measurements that you're making in the future, right?
Right. Mm-hmm. Yeah, I also think.
So I think it's important to make sure you're able to do that properly. You should read the instructions on how to maintain these quartz files properly, and clean them, and make sure to avoid scratches so that you won't have any such issues in the future.
Okay. Yeah, certainly. And yeah, regarding the myoglobin, the purging time should be the same as the vitamin B12, and we will get like the sieving coefficient at different like ultrafiltration rates for both of the conventional inside out and outside in mode. Then estimate the sieving coefficient. And I make up some data of like what I'm going to do. So for example, we have the myoglobin that we run the ultrafiltration rate at 80, 100, and 120 in both of the modes. That we got some values here. So I anticipate that when we put this number into the console, that here is a picture of the console that from Fasol's report that is from his simulation. So if we got the sieving coefficient, so like from one side and to the other side, maybe we can like get the sieving coefficient at this point of just one layer and to the second layer, and then is that the idea?
You should be able to back calculate, do inverse design, figure out what are the sieving coefficients for the two layers, and then you can then run a simulation and then figure out exactly what happens.
Yeah. That's what I thought.
Outside in versus inside out. Yeah,
right.
I think that's correct.
Right. And then the only problem right now is I really wish like I have the console foundation as Fasar as Q did. So I would like really have to study through this with Q and to learn about like how I can like back calculated this thing, and but this is just like what I anticipated to do with the myoglobin when I first get my hands on it.
So you need to know something about the dimensions, right?
The simulation model
of the membranes, right? You have a good idea what the dimensions of the membranes are in terms of thickness of the membrane, of the skin side and the non-skin side, as well as maybe the pore sizes or something. Do you have an idea, roughly?
Yeah, for this newly arrived dialyzer, they are all specified. They have all the details, except for the experimental details. There are geometry details, like how thick they are, what materials they use, and I think from their materials, I can get the pore size of their membranes. Yeah, sort of like that. I'm pretty confident.
You can get that, and you can probably estimate what the diffusion constants are, right, in each of the different layers, right?
Yeah. So I'll just plug this number into this model and simulate that, using this method. Yeah, and regarding the dash trends, so we will be like doing this same thing, but with the dash trend, and for the sample that we collected, we will just analyze it with the with the RI detector in the HPLC. So I will use so this is all makeup data from online, and this is what I'm going to do with it using the RI detector. So we will get some readings. So here, at the earlier or beginning of the elution volume, those are the higher molecular weight that will move slowly. They will be stay at the like entrance, And while the small molecular weight modules will move faster, they will like move so faster. And the solid line here is the feed, is what we feed, which is the bowl solution. And the dotted line here, or the broken line here, are the filtrate. So you can easily compare two of these and see like what kind of concentration differences of the inlet and the outlet through the RI detector. So for example, I injected the dextran T10 here, and it's about, like through the calibration, we know the elution volume of the dextran 10K is around this point. So we can get the concentration of the feed and the concentration of the filtrate, and then we can just easily compare it, and then we can get the sieving
I mean,
coefficient.
how confident are you doing this? Because it looks like there's going to be a lot of overlap for peaks.
Oh, yeah,
Right.
yeah. I'm sorry. Yeah, because
I mean, because you're doing like this, you know, you need, if you want to get a sieving coefficient, you have to have a pretty accurate representation of what
Right.
the concentration would be, right, at the inlet and the outlet. How confident are you in these measurements based on the spectra, like something like this?
yeah, this for this spectra, he's not like only using one dextran that we do. He using like from 342 up to 120K. So they are using a large span. So that's why we are seeing they are like a big area. So they are all dextran from like really small to really large of a range. But what we will get is something like this, that from like 40 to, so this will be 40, this will be 70. 40 means the 40 kilodalton, and 70 means the 70 kilodalton. So we can see like a separation of these two, and we will identify the peak, and then we can find the curve or the area, so that we know the
Okay,
concentration.
but even here you have overlap, right?
We will have overlap, but no matter what. So when we are having, when we're using only the PBS, so we will have the 10K, right? So that we only have one peak. We will be like loud and clear and one peak. But when we are using like the 10K, and let's say if you're interested in the 15K to 25K, then we put those two, they will have overlap, but we will know like which is which, like because the 10K will move faster and the 15 and 25 will move slower. Yeah.
Yeah. So in the case you have overlap, can you get an accurate estimation of the concentration based on the data? That's the question.
I wouldn't like say like yes, like I did it before, because I have not, and I will really, but like from the literature, like everybody is doing this experiment and figuring out like using the dextran as like a probe, and I will think they have a way to getting this like this, because they are, since they are overlapping, so I feel like the overlap part, they are generated by the machine, or to get approximately curve of this whole for a certain dextran. Yeah, that's what I'm getting. They will use a software to achieve that purpose. But I will have to like do the calibration and to actually see it myself. That's what.
Yeah, so you have to check and see if that works. But I think this is the one thing that I would have worried.
Yeah.
So I think for something like Dextran 10K and PBS,
it should be no problem. Yeah.
Integrate that, you can get like a concentration, right?
Right. Yeah. That's
but I am a little worried about the case when you have
like the BSA
a broader distribution. I'm not entirely certain that you would be able to get an accurate
clearance.
representation of concentration, and hence there's going to be considerable uncertainty in measuring your sieving coefficient, right?
Yeah.
I don't know, Q, what are your thoughts?
Maybe because the trial has more broader range, so 15 to 24K.
Sorry, Q, I can't really hear you. I think your voice is very faint. So it's can you speak louder?
Yeah, so because the 15 to 25K have much, sorry, much broader distribution, they may have some uncertainties in the seeding coefficient. Yeah, I agree.
Yeah, I think
Yeah.
I understand what Q said, that since we is poorly dispersed, that we have like a pretty large range from 15K to 25K, that we might have like a, so we can't we won't see like a separate peak like from 15 or 20 and 25. We probably won't see that. We probably just won't see a single curve for 15 and 25K. That's what I expected. And but for the 10K and here, I believe if we like wait only have this two dash trend, if we wait long enough, we probably can see the C separate a little bit more, because we are not separating from really small to really large, and there are a lot in between. We're only separating two of these. We might, if we, yeah, we will have to see like what the system looks like. But I thinking about like adding both the 10K and 15 and 25K together, and we
Can you explain to me exactly the experiment you plan to do with dextran?
Yeah.
Because you're dealing with different molecular weights. I just want to tell me exactly the experiment you plan to do.
Yeah. So I was thinking to add the 10K and 15 to 25K into the like the PBS, which is the just accurate aqua solution, and to the BSA, which is to simulate the blood solution. And we know that like this PowerPoint is mainly made for the Rexy 21R, but I feel like it's also applicable to the new dialyzer. I don't think they can have like a really high molecular weight clearance. I can show it back real quick. Yeah, because for the newly dialyzer, they have a really low albumin sieving coefficient. But albumin, it can range to 40K to 60K. So what I'm thinking is it will probably have like slightly better sieving coefficient than the Rex 21R, but it should be pretty similar than what we're getting. And my point is that when we're putting the 15 to 25K, even though maybe like 23 and 24, it won't pass it through, and we will only notice the 15 to 20-ish, that only a portion of it will seep through the membrane. Then we will see.
What about the 10K? Sorry, you're saying you're dissolving 10K and 15 to 25.
Yeah.
Dextran.
Yeah.
And you're saying only the 15 to 20, only 15 to 20 K Dalton will pass through. What about 10K?
It will. Yeah. I'm sorry. So this is 10K and 15 to 20-ish, and the 20 to 25 part will not passing through. And my point is it shouldn't be a problem that we. Yeah. So the idea is like when we injected the solution into the RI detector, so we were seeing a peak. So for example, let's imagine if the 10K will separate with the 15 and 20, or so we will observe like two different peaks here. They might have like overlapping, but let's just assume it has separation. Then we will be able to see the peak and the area of the curve and get the concentration from it.
Mm-hmm.
Yeah, and my point is, even though we can't capture the 20, so the 20 to 25 won't be seeping through, and it shouldn't be a problem that we use the 15 to 25K. Yeah, that's my point then. Yeah, even though part of it.
Can you go up to the previous slide? I think you missed a slide or something. So.
Oh yeah, yes.
So sorry. So you have so even the previous slide before that.
Mm-hmm.
I just want to see what is it. So sieving coefficients for dextran. So are you planning to do sieving coefficients of just dextran in PBS?
In PBS, I feel like that will give us a good idea. Yeah, in PBS only, not the.
So you can do sieving coefficient in PBS of what, 10K or 15 to 25K? Which ones are you looking at?
I would say both. That we will do both of them, but the only thing about the 15 to 25K is we know we will only get a sieving coefficient for the, let's say we do 15 to 25, we will only get the sieving coefficient from 15 to around 20-ish. That we won't get all of it to passing through together, because we know that.
And you'll be able to distinguish between the 15 to 20
with the
between 15 and 20 and 20 to 25K.
I believe so. Yeah, I believe so. Because we will have a calibration curve. We know which elution volume correspond to what kind of, like, what is the molecular weight. So for example, here will be like 20, and moving a little bit more, there will be 55, 15, and 10, something like that. If we aren't seeing the high molecular weight part, so that is not being sieving through. Yeah. Does that make sense? Yeah.
Yeah, I need to think about this. I'm not entirely certain, but I think definitely for 10K it'll work. I'm not entirely certain how reasonable this will be for 15 to 25K.
Right. Yeah. Sorry, this is like the only graph that I from literature. I haven't do any calibration, so I can give you like a more visual effect. But
can I see the next slide? Not the clearance experiment. Previous slide.
This one?
No. Next one.
This one? Mm-hmm.
Yeah, this one. Yep.
Yeah, this one is give you like an idea of like what kind of budget. So when we're using the lower lab, we probably do calibration. We probably do conventional first on PBS, and there will be about like 15 of the experiments that we do. Oh, I'm sorry, 15 injection include to complete the experiment of the conventional. Mm-hmm. Just to give you a rough idea of like how many monies we're going to spend on the usage of the equipment.
Okay, and then outside in. Okay, and now you're doing also BS. This is all PBS.
Oh, this is including
BSA.
the with the BSA. So we will have to like simulate the blood solution, but we will do this first part with the PBS first, and then the BSA. Mm-hmm.
Mm-hmm.
Yeah, and so that would be like 25 times like $13 per injection, something like that.
Sorry, so you say 25 times what, 13?
$13. So if we're doing like the whole thing, which is 50 of this, 50 of the injection.
So 50 times 30.
It will be 650.
130 times 5, which is $600 some dollars.
Yeah, $650. $650. Yeah, something.
Yeah.
Is it looking like acceptable?
That could be okay. Yeah.
Yeah, but that would be the case that we use the equipment at lower, that we don't have to purchase a column, we don't have to worry about the R detector. If it works, I think it's a really good options.
Yeah. But so you have to do a couple of calibrations with them.
Right. And the good thing is they also have the calibration dash trend. I look it up that we can't just use this. This is really poorly dispersed. So we will use the dash trend that is really specified. So T10 is actually, it's not like an average. It's just the 10K of the dash trend. Mm-hmm. So they will give like a really good calibration that we will have to purchase from otherwise. But the good thing is at lower, it seems like they have this T10, T40, that with the really specific molecular weight dash trend in their lab, they can do the calibration for us. Then we don't have to worry about to purchase additional of the material. So I think that's a good thing about the lower. And like to continue after we like put the 10K and 15 to 25K, or we can just do the single 10K to be safe. But I just wonder what the peak will look like from the calibration, and we will decided the next step. And we will measure the peak area of the 10K and the other one, and then we will get the concentration out of the peak area. And the next step will be to calculate the clearance from the concentration that we got from the 5 injection that we do.
Okay.
Mm-hmm.
Yep. See the other slides you have?
Yeah, and and that is for the zero ultrafiltration rate, meaning that what Fassard previously did with with zero ultrafiltration, we continue to do for the clearance, we continue to do the exponential decay model to get the alpha value from the exponential and then plug it in and then calculate the
Yeah.
clearance. Yeah, no problem.
I mean, I anticipate if you do zero ultrafiltration, you'll get the same results as him.
At the
If you do it in PBS. In BSA, it may be different because you get fouling.
yeah, that's the part I don't want to think about it more, because with fouling, that means there are gonna be consumption of the dialyzer, and that's why they give it us like 12 of them. I will have to like think more about it and how to like optimize the usage of the dialyzer. Yeah, but
Yeah, that's why. Yeah, that's why. Yeah. So, but I think with PBS, I mean, you just have zero net ultrafiltration, and you're probably gonna get like no difference between outside and inside out, like what bars out observed.
yeah.
Yeah, only when you have net ultrafiltration you may get differences, or if you have fouling you may get differences.
Okay. Yeah. Cool. Yeah. So for the non-zero ultrafiltration rate, I would recommend to do a no recycle, just like a simple in and out single pass mode and because the clearance is given by QB times C in minus the QB minus QUF times the C out. So basically, you're just focusing on the dialyzer, what's coming in and what's coming out, and divided by the initial concentration. So that's the clearance. So we can just do similar thing like the sieving coefficient experiment, that we use a single pass. I'm sorry. We would do the hemodialyzer mode, but we would just like not recycling back, and that would just get us pretty good idea of the clearance.
But the question is how much. The issue is you may have to use a lot of solvent, right? Doing this, how much solvent will you use?
It really depends on how accurate. So yeah, the thing about the 5 injections at certain times, so we will get it's definitely going to be worse than if we have 10 injection, correct? So we have 5 injections, so we can get like a rough idea on how the concentration is changing, but it won't be as accurate as the 10 injection experiment. I think that's a pretty same idea of the.
No, I mean you should get an idea of how much volume you can use doing this. You're going to be doing non-zero ultrafiltration. How much volume are you going to be using during this experiment, and how much dextran will you need to be then using per run, right? You need to think about that, because I thought the issue why we wanted to not go down this route was that you thought it was going to be too expensive. Each experiment is going to be too expensive.
Actually, I think that was Professor Clark's standpoint, that if we are not recycling, we are wasting something. But from what I understand, like from what I have been doing, I feel like if we don't recycle it, we can actually save more. Imagine that when we are using the hemodialyzer coming in, dialysis going this way, blood going this way, when we recycle it, the whole beaker, we cannot use it. We have to dump the whole batch because it has been diluted with the recycle, and the concentration is unknown right now. And we can't use it for the next experiment because we don't know the concentration of it. And if we only doing a single pass, so that the blood coming out here and through the dialyzer, and then we do a single pass that we just collected the single pass and we're not recycling, the concentration here is the exact same. There's nothing has been diluted or contaminated, so we can reuse it, the rest of them. It is the recycle that is more costly than the single pass.
No, well, but no. But you understand, like, so you have to, when you're calculating clearance, right?
Yeah.
When you calculate clearance, you're measuring concentration over time, over how long?
If we're doing only 5 injection, we will probably select a perfect time length to do injection at.
No. So okay. So for Farzad, when he was doing clearance measurements,
Yeah.
how long did he run his experiments to measure clearance? He ran for like what?
15 minutes.
20 minutes.
15.
How long did he run?
15 minutes and 1 minute each time step. Yeah. So this is like the 15 time steps here he get.
So he said 15 minutes. He said.
Yeah, 15 minutes and 1 minute as a time step.
50 minutes. 50.
Oh, so I'm sorry. 15.
15 minutes. Okay.
Yeah.
He did 15 minutes Okay, and what was the flow rate?
The flow rate is about 200.
Milliliters per minute.
Right. I think we can stick with 200
So
or
200
300.
times 15
It's a
is
lot of.
what? It's like 3 liters you're using
Yeah. So
per experiment,
yes,
right?
right. And that's not even including the dialysis. Dialysis are running as 500 milliliter per minute, and it's this. So it's.
This is why I want you to
Oh,
estimate.
okay.
This is why I want you to estimate how much volume you'll need to use and how much dextran you'll have to spend per experiment. Because the whole idea behind the whole ultrafiltration, why we wanted to recycle, was that we thought that if we didn't recycle, we'll be having to use like 3 to 4 liters per experiment. And if you're doing 2 grams per liter, that's like, how much money are you spending, right?
Yeah, this is mostly the dextran, the gram, the actually gram that we are putting in. But
yeah, but if you're doing B12 or myoglob, so you need to think about, you're doing clearance with ultrafiltration.
Mm-hmm.
You need to think about how much solvent you'll be using, how much material you'll be using, and whether it's economically feasible.
I see. Yeah, I will.
Right.
Yeah, get that number for you next time, for you to compare.
No. I just want you to think about this because, if you're gonna have to use like 10 liters of something, right, or whatever, I don't know. You have to use a lot of fluid and a lot of material each experiment. It's not gonna. It'll cost a lot, and it probably won't be very difficult to do, right? So you have to think about this, whether this is a reasonable thing. I don't know for dextran or for B12 or for myoglobin, right?
Yeah, I
If it
understand.
is.
I understand that.
You have to do the calculation. You should talk to Q, go through the calculation, think about it.
Yeah, I understand your point. Yeah, that should be a problem for if you're using no recycle.
Okay, next step, next slide.
Yeah, and I want to explain a little bit like why the non-zero ultrafiltration recycle wouldn't work. And for when we have like a zero ultrafiltration, so the beaker was coming in after the hemodialyzer is gonna coming back, and the losing of the toxin concentration here is gonna be decaying through exponentially when it's exiting through the hemodialyzer and have this relationship. So that's why we can just calculate it, the change of the concentration, and get this alpha value and then plug into the function of the clearance to get the clearance. But for the non-zero ultrafiltrations, we will have the concentration CT is exponential decaying because of the recycle, and then we have the volume is decreases with the ultrafiltration. So that's why the concentration is gonna like jump up by its nature. So that's why the ODE is gonna be like pretty ugly, and we can't like seem to get anything from it. And it's really hard to imply the total effect because the total effect is not just.
Is this true, Q? Can you actually imply something? Can you figure out what the clearance is based on? I mean, this doesn't seem this expression doesn't seem too complicated just looking at it here. So I mean, what is the issue in terms of implying? Sir, it's not exponential, but you can fit it. I'm just trying to understand what is the issue.
Yeah, so to express the clearance, we have to put the some function of the k. So k is equal to something, but k is located at the A as well. So maybe we need to fit.
So if you like did a thought experiment, or you ran, let's just say you have you're not doing an experiment, but let's just say you were running a simulation, right? That that represents the system that you described above,
Mm-hmm.
and you're given some data, how could you estimate the K, the clearance from this? How will the concentration change as a function of time? How will the clearance, could you estimate, could you figure out what the clearance is?
Yeah, and if we apply that the same ideology that we have K here and we have K in the alpha, which is the power.
You can do root finding, right? I'm just curious, what would it look like? What would the clearance look like over time? What would the concentration look like over time? And if you try to figure out what the clearance is, what would it look like? I mean, maybe it won't be very, maybe like, it complicated, it's just the expression's complicated, so therefore, like, it won't be very, the data fitting may not give you an accurate value of K, but I don't know. I mean, in some sense, this is like something you could do in principle, right? You can do data fitting and get a K. It's just a nonlinear fit, a highly nonlinear fit. That's the difference.
I think the problem with this expression is like we have a K here, and with the other like independent variable would be the T. And we plugged like different values of T in it, the K is still the same.
Okay, so what is known? So what is known and what is not known?
Yeah.
In this expression.
Mm-hmm. All the unknown is the K that we want to know and the T, the time. All the other thing is known. All the other value is known. And when
so then if you're given.
Mm-hmm.
Okay. So and what is the concentration? I don't understand. What is the concentration?
Yeah. When we plug in the concentration equation, like into the original mass balance, so there are no concentration here in the equations. Only the time as the variable, and the K is what we wanted. All the other is known, but they have this relationship here. It is
okay. So for any given time point, you can do root finding and find out what the clearance is.
Yes.
And then you can find out what the concentration is based on the solved clearance.
Yes. And the thing I have actually.
And so then for a given.
For a given time we have a K value, but the thing is like for the ultrafiltration rate of 75, and the blood flow rate is 200, and we the equation will become like this like relationship, and is this always going to be, the K is always to be equal to be 200, which is the flow rate. So they will automatically like see this number as 1, because we know that this is just like the initial volume. So this denominator and the numerator are pretty similar and can be close to 1 if we consider the delta T is really small. So this relationship it just gave us the K will be equal to the QB, will be equal to the flow rate of the blood. That's why I don't understand that making any sense with this model.
I mean, it's not exactly.
It's not exactly 1 this part, but when I try to like plug some numbers in it, it's just give us every time, like when we're changing the ultrafiltration rate and changing the time to 3 to 4 to 5, it always gives the value K will be equal to here 200, and that would.
Okay, and when you're doing clearance for zero ultrafiltration, what were you getting? What are the order of magnitude K? What values were you getting?
90, 140. Yeah, it's the same magnitude. Yeah, 140. Yeah.
And what was the flow rate of blood?
The flow of blood is 200.
Um, so okay, what is delta t?
Delta t is 1 minute. So this equation, like if the time is like 3 minutes or 4 minutes, it will just minus 1 minute here.
Mm-hmm.
Mm-hmm. Yeah, so in the mathematical model, so this number will be like pretty close, the exponential term here. And
I mean, Hugh, is it possible to see, I mean, given a set of flow rates in time, can you actually estimate what can you get a curve for how the concentration varies in time and what the clearance will look like?
Maybe if you have some data set like time and concentration, we can try to calculate fitting the clearance at that given time, and maybe you can try to fitting it eventually.
Yeah, I'm just curious. I don't know how I mean, you can run. I would say you don't have to do an experiment, but you should just double check your math and see whether this is actually reasonable, right? You can plot the curves of what it looks like and see, does it make any sense? Does this math actually make any sense? And based on this, can you actually extract out a clearance rate?
yeah, we can try at different time
from
points.
this, and what is extracted? Does it make sense? Right?
Yeah.
Yeah, I see.
Because I don't like this. I mean, you're just saying that it doesn't work just because it's complicated. This doesn't look that complicated to me, right? So, I mean, if there's a better reason why you think this is not working, if there's a physical reason, I'm fine with that. But if you're just saying that no, it's because it's not a simple exponential, I'm not going to do it. I don't quite agree with that logic. Mm-hmm.
Yeah, I think we can working on.
We try to figure out.
So I mean, another question is like, does it make I want to question out? No. I mean, if you measure a clearance using this recycle mode, like if you're doing a clearance under zero ultrafiltration rate, and you measure the clearance under one pass or under recycling, it'll be the same, right?
What will be the same?
Okay, so if I did two experiments under zero net ultrafiltration, I did one experiment where I just flowed into the dialyzer and then flow out, okay, and I did not recycle, so I do one pass.
Yeah.
If I measured the clearance that way, I'll get a value.
Yes.
If I do a second experiment where I do the same thing, but now whatever
Recycling?
comes out of dialyzer, I recycle back and continue over time, and I measure a clearance. Yeah. That's the clearance from the second method. The two clearances I measured from the one pass and from the recycling
should be the same.
Right? For near zero net ultrafiltration. Now, when ultrafiltration is occurring, we do one pass versus recycling. I mean, are you actually gonna measure the same thing? That's not clear to me, and you need to think about that, right?
Okay. Yeah, I'll certainly.
Now, if you're not actually gonna measure the same thing, and it's like there's like it's clearly the experiments are like looking at different phenomenon, then yeah, I mean that's fine. Then there's no point doing this, but I don't know, right? You have to think about that. Mm-hmm.
Yeah, certainly. Yeah, it's not very clear to me for now. Yeah, I will think more about that.
Mm-hmm.
Yes. And yeah, to conclude a little bit, I'll just in the next coming couple of days just get the myoglobin, see what Fasard did, and
Yeah,
then
but I mean, I think you should do the stuff that look at the clearance of B12 and myoglobin, using UV vis, right?
yeah,
Compare it with the Farzad, or see if you get the same stuff that Farzad did, and then look at what happens when you have net ultrafiltration, right?
and also can I get a go on the lower lab to start things up?
So how much will this cost initially?
Yeah,
just
like
to
I
do
said,
the
initially
calibration?
just do the calibration. Let's do 5, then $13 per injection.
So
It's gonna be
5 times
65.
13, that's $65. Yeah, just go ahead.
Okay.
Let's do the calibration and see.
Yeah, and I will probably can answer some of your graphing problem. Yeah, something like that. Yeah, I should be able to get that after the calibration. Yeah.
Yeah. Yep. And if you need, you should share some of these slides to Bill as well, so that
I'll probably
we can
just
discuss.
send our meeting to him because I recorded it. Yeah.
Oh, you recorded it?
Yeah.
Okay. Sounds
Is
good.
that a problem to you, or do you mind?
No, that's
Okay.
fine.
Perfect. All right. Yeah. Thank you for your time with me and Q, and explanation. That helps figure my mind a lot. Yeah. Thank you.
Okay. Sounds good.
See you next time.
Okay. All right. I'll catch you later.
Bye, Q.
Okay. Bye.